Okay, so hello everyone. I hope I am audible. So good evening to everyone. My name is Abhishek Pandey. I'm a Prime Minister Research Fellow in the discipline of mathematics at IIT Bhubaneswar. Today we are going to talk about week 3 assignment. So let me start. So first I will start with some basic facts. So to start with tangent planes and normal lines. Okay. So let f x comma y comma z be a differentiable function this is a differentiable function and f of x y z is equals to c be a level surface. So this is level surface S. Now if gamma of t, so this is a curve, so its coordinate is like this, j cap plus k cap is a smooth curve on the level surface S. Is a smooth curve on the level surface S. Okay. Then we can see that since this is on the level surface, so we can see this f of zt comma h of t and k of t. This is going to be c. Now let us say equation 1. So differentiating equation 1 with respect to t. Okay. So what we will get is of zt this is 0. Okay, so this because this is constant, so this is 0. Now what is this? You can use the chain rule. So this is nothing but del f by del x and dg by dt. Okay, del f by del y dh by dt plus del f by del z dk by dt is equals to 0. Okay, so this is nothing but a dot product. Okay, between what and what. So it is, let me write it in a shorter form. So this is fx I cap plus fy j cap plus fz k cap dot product with dz by dt I cap plus dh by dt j cap plus dk by dt k cap. Okay, this is 0. Okay, now this gives you that delta of f dot d gamma by dt is equals to 0. Okay, that is this delta of f is orthogonal to d gamma by dt. Okay, so what is the conclusion? So the conclusion is at every point at every point along curve gamma on the level surface. Yes, f is orthogonal to curve's velocity vector. Okay, I hope this is clear.
Yes, sir.
Okay, so now we'll see the what is the meaning of tangent lines. Okay, tangent lines. Okay, so what you do, so consider all the curves all the curves that passes through a point, so passes through a fixed point, okay, on the level surface. So consider all the curves passes through a fixed point, p naught, okay. So hence all the velocity vector all the velocity vector at p naught are orthogonal to del f at p naught, okay. So the curve's tangent line lines all lie in the plane, so all lie in the plane, this plane passing through p naught and normal to del f, plane passing through p naught and normal to del f, okay. Now now we'll see what do you mean by tangent plane. Now it is clear how we are going to define tangent plane, okay. So the tangent plane, so the tangent plane at a point p naught x naught comma y naught comma z naught on the level surface, on the level surface, say this is the level surface of a differentiable function f, f is the plane, so is the plane passing through p naught and perpendicular to or normal, we can say normal to del f at p naught, okay. Now what is the meaning of normal line? Okay, so the normal line of the surface at p naught is the line is the line through P naught and parallel to delta. Okay, so we'll see it geometrically. So, okay, so okay. Okay. Let us say this is the point P naught, okay, and the tangent plane on this point, let us say, okay, and this is your this is your del f, a normal vector, okay. So now let me write it down. So this is your level surface, this is your tangent plane, and this is your normal line. So in fact, del f at P naught is a normal to the tangent plane. Okay, one normal. So every vector parallel to that one will be a normal line. Okay. So I hope this is clear.
Yes, sir.
Okay. So we will move towards the equation. How to find the equations? Equations. Let us see. So, tangent plane, tangent plane to surface S. So this surface is nothing but f of x comma y comma z is equals to c at point p naught, let us say x naught, y naught, and z naught is, so this is fx at p naught x minus x naught plus fy at p naught y minus y naught and fz at p naught z minus z naught is equals to 0. So this is your equation of tangent plane. Okay. Also, the equation of normal line to S at point P naught, which is x naught, y naught, and z naught. Okay. So this is nothing but x is equals to x naught plus fx at p naught into t, comma y is equals to y naught plus fy at p naught, comma into t, comma z is equals to z naught fz at p naught into t, where t belongs to r. So based upon this, we'll solve some problems, but before that, we will see some a plane tangent to a surface. So this is the equation. I hope this is clear because we will use this frequently to solve the problems. Is it clear?
Clear, sir.
Okay. So plane, so tangent plane to a surface. Okay. So let f be a differentiable function. Okay, and this is the surface. S is equals to Z, S such that Z is equals to Fx, right? Be the surface. Okay, and let P naught, X naught, comma Y naught, comma Z naught be a point on S. That is, what does it mean that, so P naught is nothing but X naught, Y naught, so Z naught is basically F of X naught, Y naught. Okay, so the equation of tangent plane, so the equation of tangent plane to the surface, S at point P naught is Fx at x minus x naught, sorry, Fx at x naught comma y naught into x minus x naught plus Fy at x naught comma y naught into y minus y naught minus z minus z naught is equals to 0. This is the equation of tangent plane. Okay, and equation of normal line at P naught, so x naught comma y naught comma f of x naught comma y naught is x is equals to x naught plus f x at x naught comma y naught into t, y is equals to y naught plus Fy at x naught comma y naught into t, and z is equals to z naught minus t, so where t belongs to r. Okay, now now we'll see something. Tangent line to the curve, to the curve of intersection of the two surfaces, intersection of the surfaces. Okay, so let S1 be a surface, comma z is equals to 0, and S2 be another surface, z is equals to 0, be two surfaces, and gamma be the curve of intersection. Gamma be the curve of intersection of S1 and S2. Okay. So the tangent line will be orthogonal to both del f and del g at p naught. Okay, and therefore, so so if a line is so if a so if a vector is perpendicular to two vectors, okay, so means it is parallel to their cross product p naught, and therefore parallel to del f cross del g. Okay, so the conclusion is thus thus the equation of line PA passing through P naught and parallel to the vector del f cross del g is the desired equation. Okay, now we'll move towards the assignment problems. So the first question is related to this. So first I am explaining the concept, some concept, and then I am doing the assignment problems based upon that concept. The first question is, so question number 6. The parametric, oh, sorry. So the parametric equation of the tangent line to the curve of intersection of the cylinders. So one is x square plus z square equals to 2 and y square plus z square equals to 5 at the point 1, 2 and minus 1, okay, is question mark. So what would be the equation? This we need to solve. So solution is, so let S1, let f of x comma y comma z is x square plus z square minus 2 and g of x comma y comma z is y square minus z square minus 5. Okay, now consider level surfaces. Consider so your S1 is nothing but x square plus z square is equals to 2, means fxyz equals to 0, and S2 is gxyz equals to 0. Okay, Now earlier we have seen that equation of line passing through pre-naught and parallel to the vector this is the desired equation. This is the equation of tangent line to the curve of intersection of the curve of the surfaces. This is this is what we need to find here, equation of tangent line. So first we need to find this del f cross del g, okay, at that point. So what will be del f? So for that we need del f by del x. So del f by del x is nothing but 2x, okay. So del f by del x as 1 2 minus 1 is nothing but 2x at 1 2 minus 1. This is nothing but 2. Del f by del y at 1 2 minus 1 is nothing but 0, and del f by del z at 1 2 minus 1 is nothing but 2z at 1 2 and minus 1, which is minus 2, okay. Similarly, del g by del x is nothing but at 1 2 and minus 1 is nothing but 0. Del g by del y this one, this is 2y at point 1 2 minus 1, so this is 4, and del z with respect to z at 1 2 minus 1, this is nothing but 2z at 1 2 and minus 1, which is minus 2, okay. So the tangent vector at p naught, sorry, tangent line at p naught will be orthogonal to both del f and del g, and hence parallel to del f cross del g, okay. So this del f cross del z is nothing but, so del f we know 2 0 and minus 2, 0 4 and minus 2, this is nothing but 8i plus 4j plus 8k, okay. Now what would be the equation? So the equation of line, so equation will be the equation of line passing through P naught, which is 1 2 and minus 1, and parallel to 8i 4j plus 8k is, so this is x minus 1 upon 8, y minus 2 upon 4, z plus 1 upon 8 is equals to t. This is your desired equation of tangent line. I hope this is clear to everyone.
Yes, sir.
Okay. Now the next question is the normal line to the surface x square plus 4xy minus 2y square plus 3z square equals to 4 at the point minus 1 0 1. Okay, so this we need to find the normal line. The solution is, let f of x y z is equals to x square plus 4xy minus 2y square plus 3z square minus 4. Okay, so the surface is S is nothing but f of x y z is equals to 0, and the point p naught is minus 1 0 and 1. Okay, so del f by del x at point p naught is nothing but 2x plus 4y. This is at point minus 1 0 and 1. This is nothing but minus 2 del f by del y at p naught is equals to 4x minus 4y at point minus 1 0 and 1, which is minus 4, and del f by del z at p naught is nothing but 6z at minus 1 0 and 1, which is 6. Okay, so this is the normal line to the surface. Earlier we have seen that, so the so normal line is nothing but it is a line through p naught and parallel to this one. Okay, del f at p naught. So equation of normal line is a line passing through p naught which is parallel to this one. Okay, so we know how to find such equation. So this is nothing but, so now the equation of the equation of normal line is, so this will pass through this point p naught. Okay, so x minus minus 1, so it is x plus 1, y minus 0, z minus 1, and this is parallel to, this line is parallel to what? This line is parallel to del f at p naught. Okay, so del f at p naught is what? Del f by del x at p naught, del f by del y at p naught, del f by del z at p naught. Okay, so this is parallel to this one. Okay, so we will get that x plus 1 upon, so what is del f by del x at p naught is minus 2, so minus 2, del f by del y at p naught is minus 4. Okay, and del f by del z is 6, so you will get x is equals to 2t minus 1, y is equals to minus 4t, and z is equals to 6t plus 1. This is your equation. I hope this is clear.
Sir, one small doubt, sir.
Yeah.
Actually, first question not asking normal line, but second question asking normal line. Yes, sir.
Yeah.
But same pattern అంటే same to అంటే normal line.
No. This is not the same pattern. So for tangent line at P naught, this is orthogonal to both this one, this and this, means tangent line is parallel to this one. Okay, so you will
Okay.
get the
That
equation of line.
this is a direct formula applying. Normal line.
No, I am not applying the direct formula. So what is the meaning of normal line? Normal line, see the definition. The normal line of the surface at P naught is the line through P naught and parallel to this one. So what will be the equation of such line? We studied in coordinate geometry the equation of a
Yes,
line
yes.
passing through a point and parallel to a vector.
Yes, sir, understood.
Yeah, so this is the
But
equation. Yeah.
yes, yes, I understood, sir.
Okay. In fact, you can directly apply the formula also. Like this is the formula I've
Yes,
written.
sir, I'm asking that one. X minus x naught into fx of that tangent line that formula also applying, sir.
Yeah, yeah, you can directly apply, but this formula is coming from the definition only, isn't it?
Yes, sir, tangent plane of the surface this formula.
Tangent plane of the surface is this formula,
Yes,
and
sir.
this one, and equation of normal line is this one.
Yes, sir.
Okay, so basically equation of normal line is passing through x naught and parallel to this one. So this will be fx at x naught comma y naught is equals to t. So this is coming from this one only.
Okay, sir, understood.
Okay, now we will move towards the extreme values. So maxima and minima. So in the case of single variable, we know the results. So like in the case of single variable, so let us say at point A, if f dash is 0 and double derivative is less than 0, then A is local maxima, isn't it? And at A, if f dash is 0 and double derivative at A is positive, then A is local minima, isn't it? And if f double dash is 0 and f triple dash at A is non-zero, sorry, is not equals to 0, so then A is called point of inflection. Okay, so we will see all these things in the several variable, mostly in the we will see in the two variable case. So maximum and maximum minimum values of a function of two variable. Okay, so first we will define it. Okay, so let y be defined on a region on a region R containing the point A comma B, then so contain point A comma B, then A, yes, f of AB is local maximum value of f if f of A comma B is greater than equals to f of x comma y for all xy. So if there exists r greater than 0 such that f of A comma B is greater than equal to this for some ball centered at A comma B and radius r, obviously this ball should be contained in the region R. Is it clear?
Yes, sir.
Okay. Second one is f of A comma B. So observe that this A comma B has to be interior point. Okay. For the local maximum minimum, f of AB is local minimum f if there exists r greater than 0 such that f of A comma B is less than equals to f of x comma y for all x comma y belongs to some ball centered at A comma B and radius r. Okay. Now we'll see the first derivative test. First derivative test. Okay. So if f of if f of x comma y has a local maximum or local minimum value at an interior point A comma B of its domain, and if first partial derivative exists there, first partial derivative exists there, then fx at A comma B is 0 and fy at A comma B equals to 0. So to be the candidate of maxima and minima, the first partial derivatives at that point must be equal to 0. Is it clear?
Clear, sir.
Okay. Now we'll see the most important one, second derivative test. And after that we will solve some assignment problems. Okay. So second derivative test. Okay. So suppose f of x comma y and its first and second partial derivatives are continuous throughout a disk centered at a comma b, and fx at a comma b is equals to 0 and fy at a comma b equals to 0. Okay, then we have the following thing. Then, okay, so let me write it down. So the condition is f has local maximum at a comma b if fxx is less than 0 and f double derivative is equal to x into y square is greater than 0 at a comma b. Okay, next thing is b. F has local minimum at a comma b if so fxx is positive and fxx fyy minus fxy square is positive at the condition C is f has saddle point comma b if fxx fyy minus fxy square is less than 0 at a comma b. In D cases, so the test is this double derivative test. The test is inconclusive, at at a comma b if this thing is 0. Okay, at a comma b. Is it clear? Okay.
Clear, sir.
Okay, but one thing is there that I haven't defined the saddle point yet. Okay, so let me define it first before this one. Okay, so let me give some definition. So one is critical point. Okay, so interior point take interior point a comma b where both fx and fy are 0 or where one or both fx and fy do not exist. So such point is called critical point. Okay. Saddle point. What do you mean by saddle point? Okay. So a critical point A comma B is saddle point if in every open disk centered at A comma B, there are points x comma, let us say x naught, sorry, there are points x comma y such that f of A comma B is greater than f of x comma y, and there are points x comma y such that f of A comma B is less than f of x comma y. Okay. So the corresponding point A comma B comma f of A comma B on this surface z is equals to f of x comma y is called a saddle point. Saddle point of this surface. Okay. So such things we have seen in real variable also, like such thing we have seen in real variable, something like, okay, so you draw this graph. Oh, sorry. Okay, so you consider this graph. So something I have made this one not correctly. Okay. So you consider a graphs like this. Okay. So consider a graph like this. So at this point, you take any neighborhood. So there are points where f of 0 comma 0 is less than xy, and there are points where f of x comma y is f of at that point is greater than. So such point is saddle point. I hope this is clear, the geometry of saddle point. Is it okay?
Yes, sir.
Okay. Now we'll move towards the assignment question. Question is, so for the function f of x comma y is equals to x square plus ky square minus mxy plus 4, x naught comma y naught is a saddle point if, so the options are 4k minus m square is less than 0. Second is 4k minus m square is less than equals to 0. 4k minus m square is positive. 4k minus m square is equals to 0. So let us see the solution. Okay, so for the saddle point, so first we need to find the derivatives. Y is x square plus ky square minus mxy plus 4. Okay, so fx is 2x minus my, fy is 2ky minus mx, fxx is 2, fyyi is 2k, fxy equals to fyx is equals to minus m. So for the saddle point, oh wait, this should be, so for the saddle point, this should happen. So this point is saddle point if this is there. Okay. So let us check fxx into fyy minus fxy square is equals to 2 into 4k minus m square. So this should be less than 0. So option 1 is correct. Okay. Now the other question is, you take f of x comma y is equals to 4xy minus x square minus y to the power 4. Then 0 comma 0 is, so we need to write which point it is. The solution is, given fxy is equals to 4xy minus x square minus y to the power 4. So fx is 4y minus 2x, and this is at 0 comma 0 will be 0. Fy is 4x minus 4y cube at 0 comma 0, this is 0. Okay. So now fxx is equals to minus 2, fyy this will be 12y square, and 12y square at 0 comma 0, this is 0, and fyx is equals to 4. So fxx fyy minus fxy square is equals to 0 minus 16 is equal to minus 16. This is less than 0. So that is 0 comma 0 is a saddle point. Okay, so this is basically saddle point. Okay, so now the next question is, this is the last question. So f of x comma y is equals to x square minus 3y square plus 6xy. Okay, so we need to find the absolute maximum on the unit square. Comma y is 0 to 1. Okay, so this is nothing but this is your 0, this is your 1, this is your 1, so this is your 1 comma 1. Let us say this is a b c d. Okay, so your f of x comma y is x square minus 3y square plus 6xy. Okay, so fx says fx is equals to 2x plus 6y, and fy is equals to minus 6y plus 6x. So this is 0, this is 0, gives you x comma y is equals to 0 comma 0. Okay, so is the candidate. So since, and 0 comma 0 is the boundary point. Okay, so since fx and fy both simultaneously is not equal to 0 at any boundary point, at any interior point, therefore f has no absolute maximum, f has no absolute maximum in interior point, at interior point. Is it clear? So at interior point this is not 0, fx and fy. Is it clear?
Clear, sir.
Okay, so interior point, it cannot be absolute maximum, that cannot be the candidate of absolute maximum. So we need to check, at boundary point. Okay, so first we will check on this line segment AB. Okay, on AB. So on AB, your y is 0. Okay, so fxy becomes a function of x, which is x square. Okay, and the maximum value is 1. So g of 1 comma 0 is 1. Okay, now on BC, on the line segment BC, on this line segment your x is equals to 1. So fxy becomes the function of gy, which is x is equals to 1, so means 1 minus 3y square plus 6y. Okay, so now let us check this one. So g dash y is equals to minus 6y plus 6. So this is 0 implies y is equals to 1, and g double dash y is equals to minus 6 is less than 0. That is y equals to 1 maxima. Okay, so once y equals to 1, x equals to 1. So f of 1 comma 1 is f of 1 comma 1 is 1 minus 3 plus 6 x equals to 4 on CD, on the line segment CD. So on this line your y equals to 1, so therefore fxy is nothing but the function of x, which is x square minus 3 plus 6x, which is derivative is equals to 2x plus 6 is equals to 0, implies x is equals to minus 3, and this doesn't belongs to 0 1. Okay, so no absolute maximum on this one. Now on the line segment DA,
Got, sir.
anything?
Nothing, sir.
Okay, so on this line segment your x is 0, means f of xy is now the function of y, which is minus 3y square. Okay, and y is in 0 to 1, so this is always negative, isn't it? So
Yes, sir.
so on this one also no maxima, so the only maximum value we are getting is 4. Okay, so therefore the absolute maximum value, the absolute maximum value is 4 at point 1 comma 1. So I hope this is clear.
Yes, sir.
Okay,
Sir,
yeah,
one small doubt, sir.
yeah, tell me.
Assignment questions, actually week 3 question. F of x comma y equal to x square plus y square minus mxy plus 4.
Wait, let me write it down. So
Okay, sir.
f of x comma y is
X square plus y square
huh
minus mxy
huh
plus 4.
okay,
A point 0 comma 0 is a saddle point. If చెప్పి m values ఇచ్చారు, sir.
so we need to find the condition on m.
Yes, sir.
So this is same as this question.
Find out m value.
This is same as this question, na?
Okay. Okay, sir.
Isn't it? This question I have solved. So you need to check this condition.
Okay.
Any other doubt?
No doubt, sir.
Okay. Okay, so we are done with the this week assignment. We'll meet in the next class. Thank you.
Okay.
So I'll close this session.